Hey guys, today we'll be solving lead code number 208, implement trie. Uh, it is a medium question on lead code and it will also help out for today's daily problem if you're interested in solving this and then solving lead code number 3043 right after. Okay, so first, to clarify, this question itself is going to test you on the data structure trees. It's in the question itself that there is a prefix tree essentially, all right? And this this ties it down to how we're going to implement the tree and how we're going to use it to essentially generate a way to see whether the starting characters match or not, or whether a word has been inserted into the tree. So what I want you to visualize first is, well, essentially what we'll have is we'll have some root node. Okay, we just have some root node. We don't care about the character it has right now. What we care about is the children it maps to. All right, so if we have, let's say, A, B and C, we'll make those proper nodes. Okay, A, B and C. And let's say C, we were told to insert the word cat. Okay, we were told to insert the word cat. We were told to insert the word bat. And in this one, we were told to insert the word ape. Okay. And this is what you're essentially a very high level view of what your prefix tree should look like. Essentially, what we're trying to go and build after is this. Now, why is the root node itself not why don't we just use A as a root node? Well, because if we did make A as a root node, then we would have to make a separate tree for B. We would have to make a separate tree for C. It's a bit more convenient to just have a root node be blank and then let this map out to other 26 alphabets that might come up, right? In this case, we've used 3 already, so 23. But yeah, you get my point. Now, how do we know whether the word ends at, okay, emphasize on the ends at this particular character? If we were told ape, okay, how do we make sure, right, so that when a person enters AP, right, searching for the word AP, it should not return true, because all we've done is insert ape. We've never inserted AP just yet as is, right? All we've done is insert ape. And if you learned about binary trees or trees in general, then you know you can modify the nodes a little bit. Okay, you can modify the node over here a little bit to have essentially a flag that says I am the end of a word. Okay, so our E, our T over here as well would all say we are the end of a word. Now, if we wanted to insert a new word, right, this is where the tree itself, the prefix tree, is really helpful. If we wanted to insert a new word, let's say cap, right? If we already have C written out for us, would we make a new tree just to add to the complexity? No, right? Obviously, we would prefer to have it as simple as possible. This tree should be as simple as possible for the traversals, right? We don't want to make it such that it has to traverse through every single character every single time, because then it would be no different from just storing a hash set, right? Okay, so CAT, we have C, we have A, we have T, but we want P at the end, right? We have C and A, we are happy with that. We just have T at the end. Well, it's fine, we can just add a P over here and just mark it as is N. There's no worries about that, right? And this way, all we've done, instead of making 3 additions, we've just made 1 addition based off our previous implementation already, right? And this isn't a binary tree, by the way, not a binary tree. It is a n-nary tree, as they call it, because it can have a n number of children. More specifically, it would just be 26 in this case, but n-ary. Okay, so when we talk about n-ary trees, we don't talk about left, we don't talk about right, we talk about children in general, because there can be any, there's no way to do left right on like three people, right? We would have to have a middle as well then. So we just call it children, right? And for the purposes of this implementation, I'll make the lookup a bit quicker, and what I'll do is I'll just make it a hash map. Okay, we'll make it a blank hash map for now, but we will just have a hash map. Now let's get to the question itself. Oh wait, actually I forgot to explain the nodes as well. The nodes themselves, like I've said already, would have the I am the end of the word, and they would have their respective children. Keep in mind that we won't store the characters like the character itself into the node. Well, because it's uh, not useful in the sense that what we will have is we will have the algorithm do the iteration over the character and see the whether it exists in the tree. We don't really need to store uh, the character itself. We can just do it on the spot with the help of this hash map over here. We will just store it like this. Okay, now let's get to the node implementation first. So we will have our trie node, right? So let's just make that, let's just quickly initialize that. So we'll do no parameters, right? Like I said, we don't have a character, so we don't really need any parameters. Let's label the is n, set it to false initially, right? We don't want to make everything the end of the word. And like I said, we will have our children be hash maps. Okay, now let's get to the question template that you were actually given for this question, class trie. All right, now what did we initialize at the very start? We just had a simple root, right? So let's just make that, let's just make a blank root. That's all we need to do. Later on we'll branch out, but for now let's just make a blank root. Call the node class that we just made, right? Now let's get to the main function. So def insert, we're given a word. Okay, the word, let's say, is, for this purposes we'll do ape. Okay, simple, and it will be easy to understand. Return is none, so we don't have to return anything just yet. Now how did we, well, not how did we traverse the tree, because usually you're used to BFS DFS traversals of the tree. How do you iterate through, let's say, a linked list? Okay, how do you iterate through a linked list? Well, you have your thing on your head, right? So our head is in this case what, self.root, right? Okay, perfect. Then what we will do is we'll just go to the children. Essentially going to the children means moving to the next node. You'll see how I do that in a bit. So now for the character in word, okay, for the particular character in the word, in this case it's an insert. Okay, if there's two cases, so if we have ape, right, we will be, well, a itself, all of these are unique characters. So a, when we do a for character in word, we will go a. Okay, and we will see that a actually doesn't exist right now, right? Because there's nothing to, we haven't added anything to the list. It's blank, completely blank. So if it is not, right, if it is not the child of the root, or like the child of the level that we are on, we would have to initialize it first of all. Okay, and just initialize it as a blank node. That's completely fine for now. Remember, we don't really care about the characters, we use the hash map to do that purpose. Okay, now all we have to do is just move our pointer ahead. So we'll point to the next node. How do we point to the next node? Well, just moving to the child of the previous node. Okay, the next in succession essentially. And after we're done with this loop, okay, so it will do a first. Okay, it will do a, what we're doing right now is it will do root, then it will add a. Okay, then with this line we will go on to a itself as our current, right? then we would see P is in a child of A, so we would do that. P would now be the next current. E E would be the next current. And now that E is the next current, what did I say about ending the word? Well, we would want the end to be marked to not have miscommunication. So we will just say C dot is end is true. And that's pretty much the main part of this algorithm. The rest of it is pretty much a copy paste with a few tweaks. That's about it. Okay, like I said, we will start off at the head. We'll go character by character in word. In this one, we want to see a map, right? We want to see a map of the function in the sense that APE has to match to APE. If we give APE, it doesn't really matter. We would still say no. That's prefix. That's something else. We're trying to do search, okay? We want it to be the same exact word. Now, what was the case that I told you about? If it is not a child, right? And remember, we are not inserting anymore. So if it is not a child, what does that mean? Well, it's because it was never in the tree to begin with, right? So immediately return false because it was never in the tree to begin with. So let's say if I was given APE, BAT, I have ape inserted, okay? And I didn't have B inserted. As soon as I would go to the root's children, I would see, well, B doesn't exist as a root, as a child of the root, right? So I would return false immediately. Okay, that's the whole point of it. And the next thing, just move your pointer to the next one. And after this loop, where will we be again? So we'll be at the very last character, right? And why did we keep C dot is n? To see whether it is the actual n. So return C dot is n. This helps us differentiate between APE and AP, right? If we wanted to do a search, we would need E to have a true, essentially, because AP by itself would right now would return false, and that's the correct way we should go about it. Now let's get to the prefix part. Okay, starts, wrong spelling. Alright, same exact thing. I'll just write it out. I won't be explaining the for loop just yet. No, I'll just write it out first because it's the same exact thing. Alright, okay. If CH not in children, what did I say about it not being a child? That means it doesn't exist in the tree, right? If it doesn't exist in the tree and we were told, okay, I want you to do APE, okay? Does APE start with a B? We made a tree, right, which would have APE as is. We made a tree for that. So if we did APE and I told you, does it start with a B? Well, your answer should be false, right? And that's essentially what this should be doing. Because if we don't find a similar word, then immediately just say false. Kind of like the same thing as this, but a bit different in terms of why it's false. Because we should return immediately on the first ever occurrence. It's the same in search as well, sorry, but you get my point. It's like the first ever iteration. Your search itself could have APE whatever, and you would give an APE. It would still go through and you would have to check for E. But in this case, it always matters, the first ever thing. Right? And like I said, the first ever thing is what matters. If we get through the entirety of the n, the thing is we asked whether it starts with the thing, not ends with the thing, or is the whole word. So we said starts with, and if we exhaust the entire prefix, right, that means we were starting with the word. It's not the word itself, but we were starting with it, right? That's what matters. And that's why we retain true instead of anything else. It's because it satisfies the condition. And that's pretty much it for this question. And like I said, if you do finish this question, then I would suggest doing the daily problem for today. 3043.